A very good day to Dr. Amin. So today my group, which is group 13, will be presenting about a critique of research titled Multi-Objective Optimization of CO2 Recycling Operations for CCUS in Pre-Salt Carbonate Reservoirs, which is written by Rodriguez, McKay and Arnold. So these are my team members, me, myself, Shavin Rao, Safa, Wei Hong, Hadif, Adila and Tanusri. So for the table of content, first we have introduction, second we have summary, third we have critical analysis, and lastly we have conclusion. Okay, for this study, focus on the application of carbon capture, utilization and storage, which is called CCUS, in Brazil's deep water pre-salt carbonate reservoir. So why we choose Brazil deep water pre-salt? Because pre-salt region is one of the regions that contains high amount of reserve oil, and it produces a significant amount of carbon dioxide gas also. So this pre-salt region contains high concentration of carbon dioxide gas. So instead of releasing this carbon dioxide into the atmosphere, so the operators recycle and re-inject into the reservoir, so making the CCUS an important strategy for both energy production and environmental sustainability. So this operator, it examines the use of carbon dioxide enhanced oil recovery, which is CO2 EOR, where captured CO2 is re-injected into the reservoir. So this process serves two important purposes. Firstly, it enhances oil recovery while simultaneously storing carbon dioxide underground, helping to reduce greenhouse gas emissions. So despite the advantages of CCUS, optimizing its operation is challenging because several objectives must be achieved simultaneously. So to answer this question, the authors developed the multi-objective optimization framework using particle swarm optimization, which is called PSO. So this PSO is a computer optimization algorithm where it chooses the best solution out of several options. So this framework evaluates different carbon dioxide re-injection strategies to identify the best operating condition that maximize the net present value. So this can increase the underground carbon dioxide storage, reduce well-to-wheels carbon dioxide emissions, and minimize carbonate steering risk. Therefore, the main research question addressed in this study is, can CCUS operations can be optimized to increase underground carbon dioxide storage, improve project profitability, and reduce carbonate scale hazards.
Okay, moving on to the summary of the study. First, let's look at the aim of the study, which is to see whether native CO2 can be recycled and used for carbon capture, utilization and storage, or CCUS, together with enhanced oil recovery in ultra-deep water carbonate reservoir. So for the second part is the method. The researchers tested 481 different development designs. They used reservoir simulation and an optimization method called particle swarm optimization, or PSO, which to find the best operating strategy. Next is the result showed that CCUS could reduce the operational carbon footprint by an average of 43.5% and increase the project net present, which is 25.5%. And however, there is also a challenge. CO2 injection can improve oil recovery, but it can cause calcite scaling, which may affect the production wells. Lastly, among all the strategies tested, temperate WAG was found to be the best strategy because it is provided a good balance between economic benefits, reducing emissions, and managing the scaling problem. So that's all for summary part. Let's move on to the next part.
So next, I will be explaining about the critical analysis, which is mainly about the strengths of the article. So firstly, it will be the novel 3-in-1 evaluation framework. This shows that this is the first study in the Brazilian pre-salt to combine economics, environmental impact and flow assurance in single framework, which means that it creates a wholesome in this article. Second point will be the methodological rigor and actionable insight. These researchers have evaluated 481 simulations cases using particle swarm optimization to deliver exact values and operational parameters, which means that this study is a wholesome study and it gives a whole new point to this study. Exceptional transparency reproducibility will be the third point, which means that these researchers gives full disclosure of equations, economic assumptions, and open source models ensures complete reproducibility for others to trust the credibility of this project. Next will be the nuanced realistic carbon accounting. It clearly separates carbon intensity reduction from absolute emissions, increasing, delivering a critical reality check for the policy debates, which means that it gives a reality check of the true current nature of the environment, and this project CCUS. And next, last one will be global transferability and future outlook. This project is not only working in one environment, it can be generalized in other environments, which means that it makes useful to others also.
Alright, so next I'll be explaining on the third part of our critical analysis, which is the weaknesses. Starting with the reservoir modeling simplifications, the study uses a synthetic unisim secondary model that oversimplifies pre-salt geology, reduces fluid dynamics to just 6 pseudo-components, and also treats the rock matrix as static, ignoring the critical geomechanical risk over 30 years. Moving to the second weaknesses, which is narrow optimization boundaries. So, the skew risk and chemical costs are calculated after optimizing rather than inside the PSO loop, creating flow assurance hazards. Rigid limits like fixed WEG pairs and a 2-injector cap restrict flexible well layouts, while the stochastic nature of PSO means global optimality isn't guaranteed. The last weakness is the incomplete life cycle accounting, where the well-to-wheel scope omits transport emissions and ignores unburned methane from flaring, underestimating the true carbon footprint. On top of that, static economic modeling locks in $50 oil and constant carbon taxes, ignoring the 30 years of market volatility.
Moving to the next part, contribution to the field. First one is fills a research gap. So before this study, researchers had looked at economics, emission and scale management separately. For example, will this make money? Will this reduce CO2? So this study is the first that combine these three together. This matter because in real life, these factors are interconnected to each other. So the second one is provides practical guidance. It identifies optimal tapered work design, and it breaks down even oil price, which is 39.2 USD over STB is the minimum oil price needed so that the project does not lose the money. And the last one is negative abatement cost, which is 94.8 USD per ton CO2 reduced. So the next one is the main improvement that I would suggest is the validate synthetic model with real field data. A synthetic model is a simplified version of reality, so it cannot capture all the complex features. Without the validation, operators cannot fully trust on the result. So when we use the real data, it makes the findings more incredible and operators will be more confident. Additionally, we can improve the fluid modeling by using the more than 6 pseudo components in the fluid model. It could improve accuracy in computing how CO2 and oil meets underground.
In conclusion, Roddick and his colleagues have delivered a highly significant framework such as net present value, well-to-well emission, and cost scale management that evaluate CCUS in the Brazilian pre-salt region by balancing economic, carbon emission, and operational scaling hazard. Their most striking finding is a carbon paradox. The study proved that while optimizing AOR through tap water alternating gas injection effectively, reduce the carbon intensity of each barrel produced. It actually increased absolute well-to-well emission simply because more oil is recovered and consumed downstream. So this fundamentally challenged the industry's simplistic clean oil narrative. While we commend the methodological rigor of the study, we have identified key weaknesses. The reliance on simplified synthetic model, the exclusion of transport emission, and treating calcite skill management as an afterthought rather than a core optimization variable limit in real-world accuracy. Finally, the impact of this article is profound. It serves as a reality check for both operator and policymaker, proving that technical efficiency cannot achieve the net zero goal target alone. Therefore, for future research, we strongly recommend incorporating dynamic economic variable, geomechanical modeling, and true full life cycle emission tracking. That's all for our presentation. Thank you.